Right, now I'm going to start this with a little bit of a discussion on discrete and uh, continuous distributions. Now I want to know whether you understand the difference between a continuous distribution and a discrete distribution. Right, so let me take my notes. Right, so today we will be talking about the normal distribution in particular. Right. So before we start, I would like to talk about the density curves. What do you mean by a density curve? And then we will move to normal distributions. Basically, there can be many normal distributions that have the nature of normal distribution, but different distributions because of their parametric variations, but at the end of the day we convert them to a standardized normal distribution, and that's the core of this discussion. So we will try to understand that part by the end of the day. So before we begin, what is a density curve? Now let me open up my notebook to Right. Now, when we think about random variables, I guess you understand the term random variables. Random variables. So when we think about something that can have a value, for example, let's say we are going to toss a coin. So when we do that, we can have two outcomes, right? There are possible two outcomes, head and a tail, right? So uh, when we give a value, say that we have 1 for head and 0 for tail, what we can have as the outputs, a value, if we say that we toss the coin 2 times, then what can we have? We can have for the first part, we can have H or tail. And for the next time, we can have H or tail. Again, we can have H or tail here. So if we follow this path, we can have two H O, we can have H or tail, we can have tail or H, or we can have tail or tail, right? So if we give a value to this head, then at the end of the day, we can have 1 plus 1, 2, 1 plus 0, 1, because we gave H to be 1 and tail to be 0. So when we add these things together to get a final value for all our possible outcomes, we can have 2, 1, 1, and 0, 0 is 1. 0, 0 is 0. So we can have these values 2, 1, or 0 for a particular random variable. We call this a random variable because we gave a value, and at the end of the day we got a number, a numerical outcome for that unknown possibility, right? So that's just an introduction to what we call these random variables and what we get at the end. Now in the case of discrete random variables, let me use a different color. When we talk about discrete random variables or discrete distributions, that is what you have learned, discrete distributions, we can have countable values. For example, if we say three mangoes, it's easy for me to draw mangoes, and I'm going to copy that, right? If we say we have right, oops, better to draw something else next time. So when we talk about mangoes, so we have 3 mangoes here. 3. They are countable. If you talk about people, say your classmates, so boys and girls, so we can count this, right? So in the case of discrete distributions, we can count the number. So there's a discrete, like it says there's a distinct value, right? There is no interpretations or there is no intervals. In the case of a discrete value, the best we can understand about that is you don't have decimal values. You have direct values that says it's 1, 2, 3, 4, 5 kind of. There are no intervals in discrete values. So in the case of discrete distributions also, you have these values. How many, for example, how many balls you can choose, how many ice creams. So if you talk about ice creams, how many ice creams means you can have, like, it's just a number. You can't have 1.5 ice creams, even though you can share that. That doesn't mean that it's like a fixed thing, right? So you can have 1, 2, 3, 4 kind of. If you think about a car, you can have 1 car. You can't have 2.5 cars, right? It's not possible. So discrete random variables or discrete distributions, they always talk about these countable values. So that's about them. Now, when we move to discrete from discrete distributions to continuous distributions, the difference is you can't really say that there is a value for the particular continuous random variable. In that sense, let's say that we are going to measure the weights. Say that I'm going to measure the weight of a person, of your batchmates, one of your batchmates. So this is him, and he's a, say, fairly fat guy. Okay. So I'm going to measure his weight. And when I measured it, it was, say, 59.05 kilos. Right. Now, can we say that it's kind of, it is exactly 59.05? Is it exactly 59.05 kilograms? No, right? Because it is dependent on, no, yeah, because it depends on the sensitivity of your measure. So if you have a better measuring equipment, like an equipment that is more sensitive, you might have a value of 59.50162 kilograms, for example. So it depends on your measurements as well. And you can have more and more sensitive equipment that goes more and more decimals into this measurement. That is regarding one person, one weight measurement. But if you think about your entire class, so you have around 100 plus students. So at the end of the day, we are talking about 100 plus such values, and none of them will actually say a discrete measure. I'm sorry for using this word, but that's the exact term. You don't have a discrete countable value. You will always have a value that is sort of a measure of either a range. For example, you can say that this person's weight is in the range of 59 kilograms to 59.1. So we can say that this is his weight is in between these two, but we don't know exactly what is the value. So it is either a range or you can't really say what is the value. So in the case of a continuous variable, the thing is that you can't really say exactly what is the value. You always have to rely on a range of values. So let's talk about another example. Let's say that you are downloading, you and your friends, say you are downloading the, so what is sort of a popular TV program. Let's say that you are interested in Supernatural. I don't know how many series have elapsed now. I think it's around 15 seasons by now. So you are introducing this TV serial to one of your friends, right? So you go and tell the person that there is a very nice TV serial. So we need to, if you like, you can download it using university internet. So this is what you use internet for, right? So university internet, you go there and then using the university Wi-Fi, you are going to download Supernatural TV series. Say you have now 15 seasons. Now, let's say that the person is interested in downloading the first season, right? So I think first season, if I'm not exactly remembering right now, say that you have 15 episodes or 20 episodes, I don't know. Let's say 15 episodes, just to be clear. Now, 15 episodes. Now, this person, your friend, we'll call him Mark. Okay, so Mark. Now he's taking his laptop and he's going to download this Supernatural series from whatever the sites. Let's say that he got a direct link to download and he's downloading the thing. Now, he's a geek, sort of. So what he's doing is he's taking a piece of paper and writing down the time elapsed for downloading each of the episodes. So episode 1 is just doing a table. So episode 1, we know that it's season 1, right? So episode 1, maybe 15 minutes and 60 seconds. So minutes and seconds. And episode 2, maybe 14 minutes and 12 seconds, right? So maybe episode 3, he got a better connection, maybe a better bandwidth somehow, and maybe 7 minutes and 8 seconds. So likewise, he's just recording the time elapsed for downloading. Now, can you say that it's a discrete value? No, because you can have milliseconds, you can have more, variations to the time, and there is no exact value. But you can say at the end that maybe for a episode download, there were like certain intervals, and also you can say that for downloading, say more like for downloading a particular episode, what is the average time elapsed, right? And also in between two downloads, what is the time elapsed? Likewise, you can have different measures regarding these continuous variables. So this is a continuous variable. So time, weight, height. So all these measurements that take up to a value, but it all depends on the measurement that you take, or for measurements that you can't really take exactly. So all of these things fall under the category of continuous variables. Continuous distributions are built on these continuous variables. So we go back to the lecture. So when we try to develop, now you know that from the previous lectures, that when we want to develop a frequency distribution, a histogram for discrete variables, histogram would look like this. So if you want to develop a histogram for a continuous variable, a discrete variable, it will sound like this. So let me be a bit clear now. Now let's say girls, and if we talk about ages, so students in a school, say that in a school you have 100 students, and then 100 students, and then students who are in the age from 10 to 15, say that you have 20 students, and from the age 15 to 16 you have say 15 students. From age let's give it a larger number, say 50 students are from 10 to 15 age, and 15 to 16 15 students, and 16 to 17 say 20 students. So how many? 70, 85. So remaining 15 students are from 17 to 18 age. Now if you want to get now this is what we call this is the frequency, the occurrence of a particular given category. So from 10 to 15 age, you can find 50 students, and from 15 to 16, you can find 15 students, and so on and so forth. So the sum of all these students should be equal to 100, because 100 is the total number of students in the school. So 30, 50, 100, right? This is the total. Now, if you want to make a histogram out of these data, what you can do is you can draw the frequency here, and you can say 10, 20, 30, 40, 50, 10, 20, 30, 40, 50, and then you can give the range. Let me say 10 to 15 and 15 to 16. I'm sorry for my handwriting, but this is how I can write. Right, so 10 to 50, this is, I'm going to make bar chart like that, that is 50. And 15 to 16, you have 15. So 10, 15 somewhere here. And 16 to 17, you got 20, right? And 17 to 18, you got 15 again. So this is kind of the bar chart, the histogram that you can draw. Now, in the case of relative frequency, how do we get the relative frequency? So to get the relative frequency, we divide the frequency of this one by the total. So we go for 0.1, 0.5, 15 divided by 100, 1.5, 20 divided by 100, and again 15 divided by 100. So again, as you know, the sum of relative frequencies should be 1. Because of course, the relative frequency comes from the frequency of something divided by the total frequency. Therefore, when we add all these together, the numerator becomes the total frequency or the total, and the denominator is obviously total. Therefore, total divided by total is equal to 1. Therefore, when we sum up, this is a very important concept, sum up the relative frequencies, will get 1 unity. So that's in the case of in the case of a discrete random variable or discrete value, a discrete distribution. Now, in the case of a continuous distribution, also this thing is the same, but there's a slight difference because we have something called density curves instead of a of like relative frequency diagram. But the thing is, they are the same. For the case of a continuous, for a case of a discrete random variable, you'll have these relative frequency diagrams. In the case of a continuous variable, you'll have a density curve. So what is a density curve? Density curve is something that depicts the relative frequency in a given range. Because as I told you, the continuous variables, they don't have an exact value. So all the time, a continuous variable will have in an interval. So given an interval, there is a slight like a area under the curve that defines what is the probability of occurrence or the relative frequency of that particular thing, particular range of observing that particular range. So by that definition, the density curve is a smooth curve that approximates the histogram or a model for the distribution, and it always lies on the positive y-axis, right? So it doesn't go to this negative side of the y-axis. It will be on this red colored distribution area, and it will have a shape like this. Now, this is a normal distribution. We'll learn about that, but it is not always a normal distribution. There can be different types of distribution curves, but the simple idea is that it always density curve always lies above this positive or above the horizontal axis, and it is summing up to an area under the curve to be exactly 1. So that, I guess you can understand, when we extend these relative frequencies to the ranges, what do we have? Now, in the case of a bar chart like this, if you remember your 8th grade maths, so you remember that this is an area. So you have a little, say, 1 centimeter length and then a height. So this area is equal to whatever the value that you have drawn here. So if you have a different cross section, or say this is 1 centimeter and this is 2 centimeters, this is this height should be proportionate to the area that you have drawn here. So in another way, to make a correct diagram, you either have to make sure that always your cross section is the same, right? So in the case of a continuous distribution, this is also true. When we talk about a continuous distribution, I'm going to draw an exponential distribution. We'll learn about it. So if you think about a single value, right? A single value like this, it doesn't exist. So for a single value, the area is 0. So for a single value, the area is 0. So when x is equal to xi, the probability of x being equal to xi for a given continuous variable or continuous distribution, this is going to be 0 because you don't have an area. And there are some high-level discussions about why this is a 0, but it's not our objective here to discuss all these matters at this instance. But what you can remember is that when you have single value in a continuous distribution, the probability of that occurrence is 0. But immediately when you have a delta, like a small variation from this point, when you have something like this, a range, then you have a probability. So the probability of P, the probability of Xi being in the range of a value A greater than or equal to and less than or equal to A plus a very small value called delta, it is positive. So there is a probability for a range, but there is no probability for a value in a given continuous distribution. That is what you need to understand. So when I say this is a continuous distribution and what is the probability of X being equal to a value, it doesn't exist at 0. But when I ask what is the probability for a range, it exists. So you need to calculate the area under this curve to get the probability, right? So that's the idea. Area under the curve is exactly 1. So when we sum up the whole area, when we add up all these small pieces all the way up to the full area under this curve, that is going to be 1. Because as I mentioned, for a histogram, for a given discrete variable, you know that relative frequencies are going to be 1. So the same thing applies here. You add up all these area and they will be equal to 1. Right. So that is about the density curves and how we interpret the continuous variables and how we come from discrete domain to a continuous domain. This is the idea of the entire picture. Now let's go in to particular distributions, particular continuous distributions. The first one here is a normal distribution, and you have the uniform distribution and an exponential distribution. So each of these distributions have their own characteristics, and also they have their own equations for their definition, right? A probability density function is a mathematical expression that defines the density curve of a continuous random variable. So now you know what is a density curve. So when we talk about a density curve of a continuous random variable, a probability density function is what defines its shape of the curve. So as I told you, the probability density functions it's a density function, okay? So the function will have a value for a given X value, but you have to get the area under the curve to get the probability. Okay, so maybe when you learn further, you'll find the probability density function, and somebody might give you a value, but for a given value, the function will exist, but the area under the curve will be 0 for a given value. You need to have a range to get the area under the curve, then only a probability will be there. Now take a look at the normal distribution. This is the normal distribution, the first one. It's a bell-shaped curve. It's a symmetrical and well-shaped. Most values tend to cluster around the mean, which due to the distribution symmetrical shape is equal to the median. Now, by this time, I guess you have learned about the mean, median, standard deviation, and some characteristics of a distribution. Now, when we talk about the mean, it's actually the second quartile of the distribution. So first quartile, second quartile, and third quartile. The mean lies in the second quartile, and the mode is what divides the distribution as symmetrical means. Now, if I go back and explain that again, so when we talk about the mean, when we have a 5-number summary, you have the Q2 here, and then you have Q1 and Q3. So you will have outliers and so on and so forth. So Q2 is the mean, right? And the mode, rather the median, the median is like if you have values like, say, I'm going to just write down several values, 2, 5, 8, 7, 3, 9, 10, 11. If I have a set of values like this, the first thing I need to do to get the median is to order them in the ascending order. So I'm going to order them. I'm going to use a blue color here. So 2, 3, 2, 3, 5, 7, 8, 9, 10, 11. So I ordered them in the ascending order. So how many values do I have? 1, 2, 3, 4, 5, 6, 7, 8, right? So the median is going to be 8 plus 1 divided by 2, right? That is going to be 4.5. In such case, what do? We get the fourth value, 1, 2, 3, 4, and the fifth value, and get the average of these two. So 7, 8 is 15, 7.5. So 7.5 is the median. And the idea is that when we take 7.5, we symmetrically divide this distribution, this data set, into 2 halves. So we have 4 numbers here and 4 numbers here. So that's the idea of a median. And because of the symmetrical nature of a normal distribution like this, it divides the distribution into two halves. And because it's symmetry, the mean and the median overlaps on the same axis. So the values in a normal distribution can range from negative infinity to positive infinity, which means this particular curve, there is no connection here. That means if you zoom in, so when I draw a normal distribution, if I draw a normal distribution like this, a bell-shaped curve, right? When you zoom in, if you go and zoom in this particular part, zoom in, you will see that it is more like a parallel thing. It will go towards infinity, positive infinity from this side, and it will not touch this x-axis. Okay, the same thing is applicable to here as well. It never touches this x-axis until it reaches the infinity. So the whole curve, when you take we call this an open bounded question. I didn't use these mathematical terms because you are in the first year, I think the first semester. So when we talk about the full extent of this curve, we go from negative infinity to positive infinity to sum up all these things. These are open bounded intervals. So they never touch this curve never touches the x-axis. So the area under the curve is going to be 1. And the values in a normal distribution can range from negative infinity to positive infinity. It goes all the way there. However, the occurrence of extremely large or extremely small values is very rare. That's the case. Now, if you take a look at this curve, the thing that I have drawn here, if you take a look at these green spaces, you can see it's very small. I have even zoom in. So you can check that the probability or the area under the curve is going to be smaller and smaller and smaller and smaller as you go away from the small tail here. We call it as tail. We go further from here, we will see very small probabilities, and the same thing is applicable to this side as well. So either very large values or very small values are even non-existent because of this very small area under the curve as you move away from it. But if you are somewhere here, you can obviously see a very high probability because the area is large. Right, so this is about normal distribution. Let's go for uniform distributions as well. In the case of a uniform distribution, it shows that each value has an equal probability of occurrence anywhere in the range between the smallest value and the largest value. Sometimes referred to as the rectangular distribution, the uniform distribution is symmetrical, and therefore the mean equals the median. So in the case of normal distribution also, mean equals the median because of the symmetry. And here also, because of the symmetry, the mean equals the median. Now, uniform distribution is something like this. Now, you can see that because of this shape of the curve, when I am drawing from this green color, it indicates I'm going along the curve. Now, if I go along the curve, you can see that the curve changes, which means different values have different probabilities of occurrence. Now, if I talk about this y-axis, if I draw the y-axis like this, you can see that the relative frequencies or the values that you find here, they increase as I go along this curve, and it comes to a peak and again starts dropping. So when we think about a normal distribution, the probability of occurrence is varying. It has different probabilities as different values are taken. But when we think about uniform distribution, in the case of uniform distribution, as you go along the curve, right, it's a constant height. So for a particular value, say A, there is a probability, and that probability remains same throughout the distribution until it reaches the final value. So if you think about the area under this curve, right, it's going to be 1. And what is the height of this one? We don't know, right? We can say it's the probability of a given value. Probability, as I told you, probability of a range. It can be any range, right? So given that here, the probability is a constant value, this probability is the probability of x being greater or equal to b, the height of this rectangle, and the area under the curve is going to be this one, p, probability of this being in between this one, times b minus a, that is equal to 1, because area under the curve is going to be 1. Therefore, the probability of P being in between this one, or the height of this one, is going to be 1 over B minus A. It's a very simple distribution. Since it's a rectangular nature, you can easily find the probability by getting this sorry, this difference, B minus A. So PA in between XB is going to be B minus 1 over B minus A, and that is also applicable to any value here in between A and B. Right. So that's about it. We'll learn a bit more about uniform distribution in the future. So I'll move. Now, in the case of an exponential distribution, it's a skewed to the right. So if you remember, if I go back to your previous lectures, I guess skew to the right and skew to the left. If you have a tail that is more shifted towards your right side, we call it skew to the right. If the tail is skewed towards your left side, we call it skew to the left. So the exponential distribution is skewed to the right, making the mean larger than the median. So to give a little bit of an impression about it, this is an exponential distribution. Let me use a different color. So this is an exponential distribution. It goes like that. And what can we say about its symmetry? In fact, it is asymmetrical because it's skewed to the right. So skewed to the right. Now, mean median, again, median is the one that defines the symmetry, right? So median, I would say this side has a low, like if I compare this part and this part, this area is large, this area is small, this area is small compared to this one. So I would say the median would go somewhere here, where you balance this area and the whole area here. So median will be somewhere here. And what about the mean? Mean will be the half of the distribution. So the half means the 0.5. Okay, so if I say it will be somewhere here, so mean. So what does it say? The range for an exponent to making the mean larger than the median. So mean larger than the median means it's shifted towards this side, or in other words, when you think about the expected value of X, I think you have learned about that. So expected value of X is going to be larger than the median. So that's what it says, right? Now is 0. Right, let's go on. The range for an exponential distribution is 0 to positive infinity. Yes, it goes from here all the way here to the positive infinity. So the range is going to be 0 plus infinity. But the distribution's shape makes the occurrence of extremely large values unlikely. So, but extremely low values, they have a very high probability of occurrence. So it's more like, it's like, what can we say? Let's say dying from a, how to say, if you drink poison, right? Death is inevitable, right? So dying from poison is kind of a very high probability at here, but it may take a very very small amount of people might survive. So it is more like an exponentially distributed in the sense, just to get an idea of how things have distributed. Right, let's go on. Now we talk about normal distributions in general. The normal distribution, yes. What if the range is left skewed? Then how is the probability calculated? Okay, so for left skewed, we call, there are probabilities that are beyond your syllabus. We don't talk about these probability distributions, I think, in your syllabus. So there is a distribution like this. We call this Weibull distribution. It's sort of left skewed because this part is smaller than the other part. So there is no difference. You just need to get the range from a particular value to the thing, and then you just integrate it under the curve. There is no difference. The only thing is that certain distributions will define where the probability value is high. So for example, you can see that in the case of Weibull, there is an initial probability that is kind of increasing, And there's another probability comparative to a certain value that is also steeply increasing, but there is a range where the probability is constant. So variable distributions are used to describe the lifetime of a vehicle or even your life, human life, because there is a very consistent probability of a particular range. Say car, let's talk about a car. So the first 1,000 to 1,500 kilometers, there's a high chance that the car might break, right? It increases. And then after that, maybe up to 80,000 or 1 lakh of 100,000 or 200,000 kilometers next distance, there is a certain consistent probability. It might increase something like like a shoe, but it increases very small, in very small amounts. So after that, maybe after 250,000 kilometers or something, the car has a steep probability of failure. So this is the variable distribution. It all depends on the nature of the probability distribution, and there is no difference of calculating the probability. It's just the integration or the sum of the parts underneath a given curve. So that's it. So for the question that you have asked, the probability calculator, the same thing. You just need to get the area under the curve. So if you know the distribution, which we will be talking in a moment, if you know the curve's actual function, you can get the integration and get the area under the curve. So you calculate the probability for a given range. I guess that is clear. So the normal distribution, also known as a Gaussian distribution, because Gauss has the Gauss distribution curve, they have some connections with this normal distributions, like a Gaussian behavior is kind of at a given value you have a peak, and then you have kind of symmetrical reduction as you go away from the mean. So we call it a Gaussian distribution. Normal distribution and Gaussian, they are the same. So in an exam paper, if you receive a question saying that a particular distribution is Gaussian, it means it's a normal distribution. Okay, so it's the most common continuous distribution used in statistics, because it has been studied for many years, and people know about its function in and out about that. So for the same question, if I go back, for a variable distribution, the function is kind of complex, and you have to get the function, and then only you will be able to do this integration part, which is kind of very tedious. So we have a standardized approach for making things easy. So in the case of a normal distribution, this is the case why we use normal distribution. We have a standard normal curve. So we'll come to that in a moment. Many continuous variables in business closely follow the normal distribution, right? So as I told you, if you talk about the weights, it follows the normal distribution, because you have an average weight, and standard deviation will define it something that is distributed to the left and right, but most of the cases it's going to be a normal distribution. So if you think about the customers will come at a given time, and then they decimate in the two different directions. So it's more like a normal distribution. Sometimes you'll find an exponential distribution as well. If you think about a sale, like immediately when you declare a sale, people will come to buy things, so the number of customers will be high at a given time. But as the sale time, when the goods are not there, then the customers will drop. So it's more like an exponential distribution. But pretty much, if you think about most of the cases, when we have a large gathering of people, you will find these normal distributions, because that's why it is normal. So that's the nature. Various discrete probability distributions also approximate normal distributions. So binomial distributions, Poisson distributions, gamma is a different thing. So other discrete probability distributions also can be approximated to this normal curve. Therefore, it's easy to use a unified approach using the normal distributions, because you can kind of approximate them. The main theorem that deals classical statistical inference. Now, statistical inference, I think it is good to talk about that one before I go into the other one. Now, statistics, I think I didn't do the first lecture, but I think this one has been covered. Now, when we think about statistics, we have a population which we cannot really, holistically understand, because the population is too vast. So we have the population, and what we can do is to take a sample out of this population. So we sample out some part from the population, and we do descriptive statistics. We describe the sample. So descriptive statistics is what we do to describe the sample. So when we have five students, we declare a descriptive statistics, some sort of a mean, median, some standard deviation to describe the sample, right? And after that, right, what you actually do at the end of the day is giving an inference about the population. Inference. So we use the sample to talk about population. We call this approach inferential statistics. So we use the sample to talk about the population, infer about the population using the descriptive statistics we use to describe the sample. We talk about the population. We call this inferential statistics. Now, the probability of drawing a sample from population is what we talk when we talk about a probability distribution. So there is a probability distribution, a normal probability distribution, and there is a probability of picking certain samples out of this one. And we take the sample, we describe the sample using descriptive statistics, and then we revert back to the population using inferential statistics. And in the inferential statistics, we actually link this to the probability distribution and the inferential part. There is a theorem called central limit theorem, and central limit theorem is actually entirely dependent on this normal distribution curve. That is the link between this inferential statistics and normal distribution, because central limit theorem helps us to do the inferential statistics, and the probability distribution in the case of a normal distribution is linked with this central limit theorem. So that is the full idea of this entire thing. So the main theorem that deals classical statistical inference has a close relationship to the normal distribution. So right, now let's move on. Now I want you to do something. Take 10 minutes. You have this data. The data in the table represent the amount of soft drink in 1,000-liter bottles filled on a recent day. So that 10,000 liter bottles means, which means like the sum of these things is 10,000. So 10,000 bottles, that's it. So 10,000 bottles, this liter, just ignore that. 10,000 bottles filled on each day. So amount of fill, so you can see that they have a range. So less than 1.025 liters, and there are some ranges. So, and then 1.080 above. You can imagine it's like a Pepsi or Coca-Cola bottle, 1 liter bottle. So you have 10,000 bottles, and maybe the liter amount in that bottle varies like that in a given bottle. So these are the ranges and these are the frequencies. Take 10 minutes to like write this table, or look at the table and try to get the relative frequencies of these things. You can use Excel or your calculators or whatever. Using calculators is also easy. Take a moment to calculate the relative frequencies. Please take 10 minutes and do that. I will come to the next slide. Right, I'll just help you because we will need some time. Okay, so I'm going to annotate the value here. I guess you can, if you can see me, just say thumbs up. Right, so you have 10,000 total. So when you add them up, you should have 10,000 total. Therefore, when we divide by, when we want to get the relative frequency, what should we do? We need to divide this by 10,000. Give me a second. Right. So relative frequency, can you hear me? Can you see my writing on the screen? If you can, please say thumbs up or something. Yeah. Okay. Thank you. Right. Right. So the relative frequency, 48 divided by 10,000. So just to be clear, it will be something like very small value, right? And again 122 divided by 10,000. So it will go like 4 decimal places, and so on and so forth. 325 divided by 10,000. So you can actually, it's a very simple task. So you can get those values, and then let me clear my annotations, clear all drawings, right? Now the next thing, using the data, calculate the relative frequency of the amount filled, develop the histogram for the given data. What can you say about the distribution? So develop the histogram for the given data. I have done that for you. Now this type of a relative frequency diagram or a relative frequency histogram will be there for you. So these ranges indicate these brackets. If you are not familiar with this one, actually it's very simple. This square bracket here, this thing indicates that in the range you can have this value, and the round bracket indicates, this bracket indicates that the value will never be equal to this one. So when I write something like this, it means the value is greater than or equal to this one, but less than to this value, because of this bracket, it indicates it will be never equal. So that's the notion. So if I say two brackets like this, it means the value will be greater than equal to this value and less than or equal to that value. If I say 5 bracket this like this, so this is the notation. And if I say round brackets, it means this will never be equal to this value at the end. So this indicates here 1.025, 1.03 likewise. So it goes like that, right? So this is the frequency, relative frequency diagram that you get, histogram. If you draw the center part of this columns, this bar chart, these bars, you can see that it follows the normal distribution, right? So that is how the values are given. So you can see that it follows a normal distribution curve. And for the above data, the list, let me clear all drawings. For the above data, the first three theoretical properties of the normal distribution are approximately satisfied, yes, because you have a mean, median following the same axis, and it is symmetrical, it follows a bell shape. However, the fourth one, having an infinite range, is not, because you have, you can't have negative infinity and positive infinity bottles, right? There will be obviously there will be an end to this. Even the end will be actually the given bottle being a certain size, so you can't exceed that particular value. So it will always be not that infinite. So it will be a finite range anyway. The amount filled in a bottle cannot possibly zero or below. Nor can a bottle be filled beyond its capacity. So that's what I said. You can't go beyond that and go to infinity, or you can have negative infinity by, it will not happen. From the data table, you see that only 48 out of 10,000 bottles will be expected to contain 1.08 liters or more, and an equal amount are expected to contain less than 1.025 liters. So it's very small amount. Now, this is from this distribution, what can we say? Most of these business problems, that you will encounter will be following this type of a curve. And most of the time, what you will be end up doing is trying to understand a normal distribution, right? Okay, now this is the part where we learn the theory part of probability density function of the normal distribution. Now, if I go back to the previous slide, please. This is a very important part. Please pay your attention to this. Now, I did a mistake. I kept these open spaces here. These open spaces should not be there, because I'm talking about continuous distributions, because I have 1.03 immediately after 1.03 round bracket, and this is a closed bracket, which means it is like there's no space here. It follows like immediately like that. So if I just show you that I don't need this spacing, so that's what it means. It should have been filled like this, right? And also same thing goes here as well. Now I think you can understand that part. Now when I draw the normal curve on top of this curve like that, sorry for that tremble. Now when I draw this one, this particular curve should have a function. It should have a function, right? So if you go back to your O-level maths, you know that if you talk about ax square plus bx plus c, this quadratic function, for any given quadratic function, the distribution would, the curve would look like this, right? So you can say ax square plus bx plus c, depending on the parametric values a, b, c, the position of this curve and how it looks like, and the variations can come depending on these parametric values a, b, c, and x is just the variable, right? So it's a generic equation that describes the quadratic function ax square plus bx plus c, but you can't use that quadratic equation to describe any other function, right? So when we talk about parametric curve where b and c are 0, these two are 0, then we know that the curve should go right like that, because there are no b and c. So x, depending on the x, it will be symmetrical along the y-axis. But this curve would still be following the parabolic shape, the quadratic function and all. So that is what a model is. We give a generic equation. Depending on the parameters, the curve will change, and it will have different positions, different intercepts, different different shapes. But following the generic shape, it will have different variations to the shape. That is what a model is. Now, when we talk about this bell-shaped curve, this particular bell-shaped curve like this, it has a function. So this function, this particular function goes like this: 1 over square root 2 phi under the square root, and then sigma is the standard deviation of the population, e exponential e to the power negative half, and inside this one you have x minus mu divided by sigma square. So this is the function. Okay, so x minus mu divided by sigma square times negative half, this whole expression to the power e, and that is multiplied by this fraction, this coefficient here, 1 over square root 2 phi sigma. So this is the function, the generic function, like the ax square plus bx plus c. This is the function, and depending on the mu and sigma, you will have different different shapes, different positions for this bell-shaped curve. Differences, you can find differences in curves, but the generic shape and the characteristics will prevail. So this is the function itself. Okay, so let's go back to the next slide. I think now it is clear. So this is the function. The probability density function for the normal distribution is given by this 1 over, sorry, is it the function for any? Yes, it's the function for any normal distribution. This is the function. So the probability density function for the normal distribution is given by this equation: 1 over square root 2 phi sigma e to the power negative half x minus mu divided by sigma square. So this is the function for any normal distribution. And the good thing is E is a mathematical constant. There's a value 2.71828. So it is not actually it's not a it's a continuous decimal. It goes, it's an infinite decimal. And also phi, you all know that phi is not an exact value. It will go and go on and on. But we can, for all practical purposes, we can keep these values for E and phi, but they are constant. That's the main thing. But the mean and the standard deviation are the population dependent values. Both E and phi are mathematical constants, whereas the shape of the distribution is solely governed by mu and sigma, because these are constants. Only thing that the same thing, like the case of ax square plus bx plus c, a, b, c will define the curve, right? So similarly, in this case also, 1 over square root 2 phi sigma e to the power negative half x minus mu over sigma square. This curve, the shape of its distribution and all these things will be governed by mu and sigma. So mean and the standard deviation of the distribution are the most important thing when we discuss about the normal distribution curve, the shape of the curve, because that is generic. It's like a fingerprint for a given distribution. When you have a mu and a sigma different values, then you have a different curve, right? No need to remember this equation, but it's good to remember it if you can. Like there's no harm, but it's not a it's not a mandatory requirement. This curve is not. We don't use this curve for calculations, but it's good to know this one because you understand the next step that I'm going to do when I show you. So any value of the continuous variable where negative infinity to positive infinity, these are open bounded functions. So I think this is the first semester and you haven't learned about these mathematical bounds, I guess. So when you do the integration, you have certain boundaries where the function is defined. So these are open bounded functions where it goes from negative infinity to positive infinity. So within that range, the function is defined in any given x value, their function exists. But when we talk about other stuff, like there are step functions where that particular function is defined on a given range. So they are different things. But the good thing about the probability density function for a normal distribution is it defined on the open boundary from negative infinity to positive infinity for any given positive value. So, right, now let's go to the next step, which is variable transformation and standardization. I kept that slide as an empty slide because I want to write something here. Right, now this is a very interesting thing. Now I'm going to talk about this variable transformation. Let's say let's say that you have something like a set of weights, right? So a set of weights, I'm going to write down weights, say this weights in kilogram. Say that I have 60, 65, 75, 80, 81, 90, 100, 1, 2, 3, 4, 5, 6, 7, say another 100, and then another 85. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 60. So there are 10 weights. So maybe your classmates or some other people. So there are 10 weights here. Now, say that you need to compare these with some other weights. Say that with these weights, so these are weights, we have heights, right? Heights. So heights, so this is a different set. And then for heights, we have a different set. Say 150 centimeters, 120 centimeters, 135, maybe 140 and 165, 153, 1, 2, 3, 4, 5, 6, 145, 733, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 145, 10. Right. There are two measurements. Okay. Now, if you want to give a scale to this, it's difficult to give a scale because you have, the weights will be in a different scale, maybe from 50 kilograms to 150 something, and heights will be somewhere from 120 to some 170. So there are two ranges, right? What we can do is we can transform these values. Maybe if I divide, now this is the condition. If I divide the each distribution value by the maximum, what can I get? I'll get a range from 0 to 1, right? Because when I divide the smallest value by the maximum value, so what is the maximum value here? It's 100. So if I divide each value by 100 for weights, what do we get? 60 divided by 100, it's going to be 0.6. 65 is going to be 0.65, 0.75, 0.8, 0.81, 0.9, and 1, 0.85, 0.6. So what can I get? I can get a scale that ranges from 0 to 1, right? So any number of weights, any number of observations, if I divide it by the maximum value in that distribution, I'll transform that distribution to 0 to 1 range. And if I do the same thing with heights, if I go with heights, if I divide it by the maximum value, what is the maximum value? 165. I can't really say what is the decimal value. You can check that out. 150 divided by 165 and so on and so forth. By the time I reach the maximum, I get 1. Again, I have transformed this range into 0 to 1 range. Now, if I give this thing, this is a very important thing when you learn in machine learning or something in the future, and also other transformations, you can see that we have immediately transformed the entire distribution to 0 to 1 range. So we can transfer any distribution that has positive values to this range, 0 to 1. So simply what did I do? I just divide these values by the maximum value in the distribution. So that's a transformation from 0 to 1. I converted those values to 0 to 1 range. So the same thing happens in your computer screens as well, because computer screens understands only values, discrete values from 0 to 255 pixels. So this is 2 to the power something. So what do we have? We have the camera. So this is the camera, and this is the person who is doing the camera stuff, cameraman. And there is a nice flower. So there will be colors, and he will be recording them as RGB, red, green, blue colors. But the computer doesn't understand the ranges of colors. It only understands the 0 to 255 values. So say that there's a red color stream, and what it does is it says this is going to be 0 and this is going to be 255. It transforms all these values to 0 to 255 pockets, discrete values, and then put into R value and G value and B value. And that is why you see those pixels when you zoom in. You can see these kind of small squares with distinct color values that ranges from 0 to 255. That is another variable transformation. So all these transformations are done to standardize the thing, because when we do the division by maximum value, we know that the distribution is going to be from 0 to 1. When we do that transformation that I showed you, 0 to 255, we just simply know that it's going to be from 0 to 255. There's another distribution that we do. We divide the whole thing by maximum minus minimum. So if we have, say, minimum value 1, 2, 3, 4 something, maximum minus minimum is kind of the range. It's the range. So we divide this value from the range to get another transformation, and that also will be giving values from 0 to 1, because when the minimum value comes, maximum minus minimum, the transformation is like this: value minus minimum value divided by maximum value minus minimum value. So at the minimum value, minimum minus minimum is going to be 0. At the maximum value, maximum minus minimum divided by maximum minus minimum is going to be 1. So again, the transformation from 0 to 1. Now here we have 0. In the previous case, when we divide by the maximum value, we don't have 0, a very close value to 0, but we don't have 0, because minimum value will be, if it is not 0, this is always going to be a positive value. But in this case, you obviously transform into 0 to 1 range. So that is what we call a variable transformation or a standardization. Now, in the case of normal distribution, now you asked me a question whether that particular equation is any normal distribution. Yes, I told you that it is a characteristic equation for a normal distribution. But given different mu and sigma values, you will have different normal distributions. So you can have a normal distribution like this, and then you can have another normal distribution that goes like this. And also you can have another normal distribution that goes like this. So you can have these type of multiple normal distributions, but all of them will have the same equation. But the problem is, when you are given with these type of different distributions, depending on mu and sigma, it will be a very tedious process for you to do the integration and get the probability. I told you it's not the function only. You have to do the integration and get the probability. And not only that, getting the function itself is extremely difficult, because you have to fit the curve and then do the mathematical fitting to get this curve, like ax square plus bx plus c. You have to fix that curve to that normal distribution curve. So that is a very tedious task, and it is not possible to use such a task in your day-to-day life, because there is no point of using it, right? So let me tell you something, an example. If brushing teeth is something very complex, like you have to do this and that, and then follow this procedure, that procedure, toothpaste first, and then go to the brush, and brush has to be dissolved in 104-degree water, hot water, and then do this clearing, this and that. Nobody is going to brush teeth in the morning, but of course most of you don't brush your teeth in the morning, right? But the thing is, brushing teeth is a very simple process. You just take your brush, maybe clean it, and then put your toothpaste, and then just brush it. So that's a simple process. Simple processes are very easy to implement. Now, if even how valuable function is, valuable normal distribution is, you can't use it because the process is tedious. You have to fit all these curves again and again, find the parametric values, and then go back and do the math. It's kind of a very long process. To avoid that one, we have this transformation. The transformation is, if you now, this is where it will be valuable if you remember the curve function, the typical function for normal distribution. It goes like this: 1 over square root 2 phi sigma, and e to the power negative half, and inside this one x minus mu divided by sigma square. Do you remember that? So this is the function. Now what they do is, we take this x minus mu over sigma and make this one z. So this is the normal transformation, standard normal. So what do we do? The characteristic normal distribution has a symmetry above along the axis mu. Mu is the mean, right? It is symmetrical along mean, and it has a standard deviation of sigma. So sigma will define this spread, and also the longer spread. We'll talk about this 1/3 rule and etc. So sigma is a spread. Now, when we convert this x minus mu sigma as a value z, you can understand that there should be certain boundedness for this z value, because you can see it's always divided by sigma, and there's a value x minus mu, kind of a difference between the x, the given value, and the mean of the population. So this is the variable transformation. What do we do when we have a value? We just take the mean of the population, x minus the population mean, divide by sigma. We'll do this transformation, and this transformed z value will be lying in negative 3 point something to positive 3 point something, right? So that means we transform all these normal curves, all of these normal distributions, all these different normal distributions into something of a given range that goes very nicely like that. And this range will include the symmetry mean, but that now mu for a given value is going to be transferred to 0. Mu will be transferred to 0, right? Mu is going to be transferred to 0. And because mu minus mu is going to be 0, right? And when we think about the distribution, for a normal distribution, there is sigma. So this is mu minus sigma, right? So mu minus sigma will have a value, and also there will be another value. This is mu plus sigma. And then there is mu minus 2 sigma, and there's another value, mu plus 2 sigma, and so on and so forth. So when you transfer this to a value in the range of negative 3 and positive 3, what do we get? Mu minus 3 sigma is the maximum kind of the value that, that's kind of the very end range that you can find for this distribution. Mu plus 3 sigma will be somewhere around 3, and mu minus 3 sigma is going to be negative 3, because mu is going to be 0 and sigma will be transferred to 1. So the whole distribution, any such distribution like this, as I showed you by what we do with the transformations, any such distribution will be shifted to this and this. Any distribution can be transferred to this standard normal curve by doing this transformation, x minus mu divided by sigma, right? So that is the idea of that. I'm not going to clear this one. I'm going to save this thing, save it as a PNG. So let's clear drawings, and then I'm going to go for the next slide. Right, now let's understand this one with a little example. You have designed the Video Hub website, a social networking site that targets college students. You must make sure that the exclusive content, daily videos, can be quickly downloaded and played in a user's browser to attract and retain visitors. Download time, the amount of time in seconds that passes from the first linking to the website homepage until the first video is ready to play, is both a function of the streaming media technology used and the number of simultaneous users at the website. So how many users, it's like YouTube, how many users are there, and you are just playing it. The more the traffic, it's difficult to load it. That's the idea. You open web browser on a PC at the corporate office of Video Hub and measure the download time. Fast data indicate that the mean download time is 7 seconds and that the standard deviation is 2 seconds. Approximately two-thirds of the download times are between 5 and 9 seconds, and about 95% of the download times are between 3 and 11 seconds. The download times are distributed as a bell-shaped curve with a clustering around the mean of 7 seconds. How could you use the information to answer questions below? Now, the first thing, when you get a question like, or a description like this, you need to understand what is the distribution. So you have a mean, you have a standard deviation, and it specifically says it's a distributed curve as a bell-shaped curve. So, and also there is another saying 95%. There's a rule about normal distribution. I didn't mention that at the beginning because I think it's important that you understand normal distributions to get an idea about this rule. There's a rule for normal distributions that 66 point something lies in 1/3 of the distribution, and then 97.5 lies in the 3 sigma range. So 95% means here is that range. So which means that you can actually say this is a standard, this is a normal distribution. There's no standardization, it's a normal distribution. So the first thing you have to do is convert this to a standard normal distribution, and after the standardization you can get the values to do whatever the answer the question. So what is the question? What is the probability that the video download time for the Video Hub website will be more than 9 seconds? Now let's try to understand the question, and while doing that, let me first close this one, come back. Right. So the question itself says, I'll go to the question and get this one. So we have designed the video website. I'll write down the values. Now it says, and measures the download time. Past data indicate that the mean download time is 7 seconds. So mu is going to be 7 seconds, and the standard deviation is 2 seconds. 7 seconds, 2 seconds. Approximately two-thirds of the download times are between 5 and 9 seconds. So which means if you draw the curve, because it says it's a bell-shaped curve, if you draw the curve, okay, it goes like this. Mu is 7, and 95% of the download times are between 3 and 11 seconds. So if I go to 3 and 11, 95 of this is there, and standard deviation is 2 seconds. Right. Now what I'm going to do is I'm going to standardize this curve first. So you have a normal distribution, of course, by looking at this one. So what I can do is transferring this to a normal distribution, to standardize normal. So how can we do it? Z is going to be x minus mu divided by sigma. So when I convert this to that, you will get a curve that goes like that. But now the center is 0. 7 will be transferred to 0. 7 will be transferred to 0. And 3 is going to be what? 3 is going to be 3, x is 3. 3 minus 7 divided by 2. And 11 is going to be 11 minus 7 divided by 2. So that is how your normal distribution would look like. But if you go to your Moodle, in your Moodle, let me see. In your Moodle, if you go to your Moodle, there is something called standard normal Z table. Right. So standard normal Z table means this, as I told you, it's difficult to integrate the thing again and again and again. So because of that, we have standardized this curve, and any probability that lies below a given value is given in this table. So for example, this Z value is the value that you have just calculated. Let me shift it to here. Now this Z value 0, right? This is the Z value, right? So these are Z values. So Z value 0, let's look at the table. So in the table, Z value 0 is 0.5. Yes. So how come it become 0.5? Because when you go back and say that this is Z0, check to the left of you, there's a half. So the area under the curve is going to be 0.5, right? So let's go back and see when Z is now, what is it? Z is, I'm going to do this one. Now, what is the value here? 11 minus 7 is going to be 4. 4 divided by 2 is going to be 2. Now, this value is 2, right? What is the value? Z less than 2. Let's go and see. Z less than 2. You can see that the curve says the Z value, and then to the left, you have this area under the curve. Z value is 2. You have 97%, 0.9772. So the area under this part, I'm going to use a different color. So the whole area here is 0.9772, right? So likewise, that is how your Z values were given. In your A levels, you have the Z values, right? Some of you might get 2 point something, some of you get 1 point something. So these values are Z values, Z score. So Z values come from that transformation. So if you in your A levels, you have a certain score for, let's say, for physics. Sorry, yes. Somebody asked me. Yes, what is it? Just a message. Yes. Then what is the 95% in the question? All right. Right. So 95% means, that's a good question. Actually, 95% means what can you say? 95% of the download times are between 3 and 11. I just took less than 11. There's a part for the less than 3, right? So you have to get the, I'm sorry for this screen time issue because of some problem. I need to go back. Yeah, it was not properly done. So in the question there is 95%, right? So this 95% is between 3 and 11. I just took the probability of x less than 11. So what did I do? Probability of x less than 11, I transform this x to a standard normal. So how did I do? Probability of x minus mu divided by sigma, that is going to be x minus the mean is 7, standard is 2, less than 11 minus 7 divided by 2. So I got the value probability x less than 2 as 0.9772. But actually it says 3 to 11. So what should I have? What should be the value? I should have taken, instead of this one, probability of x, this thing. So if I want to get this one, I should 3 minus 7 divided by 2 x, 11 minus 7 divided by 2. So actually the value should have been negative, this is 4, negative 2 x, positive 2. So how can we get it? Because the curve only shows values to the left side of your Z value. So how do we get it? We actually get this one first and then minus the other value. So basically this is going to be the probability of x being less than 2 minus probability of x less than negative 2. Draw this curve, you'll understand, because this is 2 and this is negative 2. So you just take the full one and then minus this part will give you the probability in between these two. So px less than 2, we got 0.9772 minus x less than negative 2. You go to the curve, x less than negative 2 is going to be 0.228, 0.228. So 0.0228 will give you a value, say this is what, 12.84624.725.9. So this is what approximately 95% says. So that's beyond the, the question has a different thing, but then what is, all right, understand, thank you. Right, so that is how it is. Now, in the case of your Z values, well, that's what I was talking about in your A levels, what was your Z value? That was calculated by, I think you have economics and other subjects, right? I'm not familiar with that, but say that you have some subject, your score, and then the mean value in that district, and then you have the sigma for that district, so z value for that. And actually I think this mu, I don't remember, this is calculated as district values and then get the z value. Oh, I don't, because that comes because of the central limit theorem. You can have the island wide, I think the cutoff comes from z values in the district, and the island wise z, I don't remember how it is calculated, but the z is simply this one. You have the value. You can have z values for different subjects as well, because say that a particular subject is difficult to all, then if you get a better score there, you have a higher z value, because the mean of that particular subject will be less, because it's difficult to most of your group, so you will have a higher z. So but actually that's an exam dependent thing. This if you have scored well, you'll get a better z. Those who got a smaller z, or people who could not get a better z to enter the university, that doesn't mean really they are bad, or they can't do anything, because actually that depends on that particular subject score. That is why in the university we have a GPA system, because we have, for each semester we have different GPA values, and that for all 4 years your marks will be accumulated. So that will be that will govern your class and all. But so if you perform well continuously, you will get a good mark. But in the case of A levels, if somebody is sick during the A level exam, then obviously if he or she can't perform well, then he will lose the Z, because all for 2 years there are no way of getting the Z, some accumulation to this Z value. So that's the difference there. Right now, I'll do something. I will not answer this thing. Where is it? Sorry. I will not answer this particular question. There is a set of questions here. Now you can find this one in the reference textbook. This is directly from the reference textbook. So you can go to your reference textbook. It is available in the Moodle. So you go to the Moodle, you have this reference textbook, and in the page number 220, you can find this question being done. Right. Please go to your textbook and read and try to do that. And then from, I think in the next lecture, I'll be conducting the next lecture. I will go deep about these normal distributions and other calculations, and particularly the continuous distribution. In that lecture, I'll be talking about these questions and in detail. So first you try doing this, looking at the textbook, reading the textbook, try to do this and come up with your answers the next lecture. And then I'll start from here, from this where I left today. And from there, I will talk about this in detail. Okay. So I'm not going to do it today. I'll be doing it next week. So please try this one at home and come to the lecture. In the tutorial, I think Ms. Rasika will be doing the discrete distribution tutorial next week. So it will be fine. In the class, I'll be starting with this and continuing from there. Please do this at home. Refer to the textbook. It's already there. And then there's the standard normal Z table as well. So refer to these two and try doing this by your own and come to the next lecture. Okay. So if you don't have any questions, we can stop the session here. So let's meet next week. Okay. Bye.